All right, so we're going to talk about how we describe motion. Specifically, we're going to look at displacement and total distance. Okay, so basically motion is the change in position of an object with respect to its surroundings within a given time interval. We can describe that mathematically in terms of displacement, distance, velocity, acceleration, speed. So there are many different ways for us to describe motion. Understand, though, that motion, the way we describe motion is always in reference to some other comparison point or reference point. So, for example, if you are sitting in a moving car, you are not in motion relative to the car, right? You're sitting in the car, you're not moving. Now, the car is moving relative to anything outside of it. So, say I'm an old lady sitting on a park bench and you go by in the car, your car is moving relative to me where I'm sitting. The objects outside the car are also are moving relative to you. So if you're sitting in the car and you're driving by, the old lady on the bench or trees or anything like that, in reference to you, those objects are moving as you're going by them in the car. Now, if you think about, say, for instance, the trees sitting there, okay, some folks might argue that if you're standing right beside the tree, you're not moving, the tree's not moving, there is no motion that can be described. But that's actually incorrect because the tree and you even being stationary are technically moving relative to, say, our sun or the other planets in our solar system, because we are stuck on Earth and Earth is orbiting around the sun and it's also rotating on its axis. So motion is very relative and you have to always know what the reference point is. All right, so let's look at distance versus displacement. All right, distance is the scalar quantity, which means the quantity that's just going to have a magnitude, no direction associated with it. Displacement is going to be the vector quantity, so it's going to have both a magnitude and a direction. Okay, so if you look at this little diagram down here, basically you see that distance is adding up all these little points, okay, all these little distances that are traveled all along from beginning to end. So you're going to add all of these segments up. There's no direction, so there's no positive or negative to mess you up. You just literally add them all together. Displacement, however, is the shortest distance between the 2 points. So that is defined as the change in the distance or the displacement, however you want to see that. So you're going to do final position minus your initial position. So if you see on here, our initial position is over here, final position is over here. So we're going to do final minus initial. Now you should see that the displacement is much less here than the total distance traveled. Okay, so now let's go look at some applications of this. All right, so just in case you weren't able to get all the information down, I made you guys a little summary chart. You can pause it right now if you need to look over this. Let me just make a couple points here. Okay, this little lovely little crazy looking E, that right there just means sum. So it's basically telling you take all the individual distances, however many they may be, and sum them all up. All right, over here, a lot of times you'll see a vector quantity with a little arrow on the top of it that indicates that it's a vector quantity, kind of helpful, but you won't always see it like that. And so we are doing final minus initial position there. All right, so Tima runs 3 meters east, 4 meters west, and then 10 meters east again. What's the total distance traveled by Tima? All right, so if you'll remember, distance does not, it's a scalar quantity, so we don't really care about the direction. I like to sketch things. So first, Tima runs east, so this is east. She does that 3 meters. Then she runs back west for 4 meters. Then she turns around again and runs 10 meters east this way. Okay, so for total distance, we literally just add these up. 3 plus 4 plus 10. We don't care about the direction. So this is going to be 17 meters. So Tima traveled a total of 17 meters. All right, now displacement is going to be your final position minus your initial position. Okay, so if we were to look at this in that manner, okay, if we say that our starting point right here is 0, okay, and then we went this way, then we went back this way, then we went all the way over here, and looks like we ended at positive 10 meters. So we started at 0 meters over here, and we ended at 10 meters in the positive direction. So now we just do final minus initial. So we got 10 meters minus our initial 0 meters, and that gives us a displacement of 10 meters in the positive direction. You don't have to put the plus sign. If it's not there, it's understood that it's positive, but you can if it helps you out. All right, and last one. So the front door is 15 meters from the mailbox. Colson runs from the front door to the mailbox and then back to the front door. What's the total distance traveled by Colson? All right, so again, I like to diagram. So here's Colson at the front door. I'll put front door, okay? And then here is the mailbox over here, okay? So we know that the distance between the front door and the mailbox is 15 meters. Okay, we also know that Colson goes from the front door to the mailbox, so that's 15 meters, and then he goes back to the front door. So that means he traveled 30 meters. Okay, that's his total distance. Total distance does not have a directionality to it. Okay, now it wants the displacement. So again, Colson ran 15 meters to the mailbox and then 15 meters back. Okay, so if we label this as the initial position, which is 0 meters, and then the final position is also at 0 meters, if you were to do final minus initial, you would get a displacement of 0. So Colson's displacement is 0, but he actually travels 30 meters.